When dealing with high inrush currents, such as those experienced when starting servo motors, it is generally advisable to use fuses that are larger than the continuous current rating of the motor. Fuses are designed to protect circuits from short circuits and overloads, so a fuse that is too small may blow prematurely when the inrush current is drawn. The recommendation to use larger fuses is likely based on the fact that the inrush current of servo motors is significantly higher than their continuous current rating. Using smaller fuses can lead to premature blowing and disruption of the machine's operation. The argument that larger fuses are not appropriate stems from the misconception that a larger fuse will allow more current to flow through the circuit, potentially damaging the equipment. However, this is not entirely accurate. A fuse is a protective device that melts and opens the circuit when the current flow exceeds its rated capacity. A larger fuse will simply allow a high current to flow for a short duration before it opens the circuit, which is often necessary to handle the initial inrush current of servo motors. The best practice for fuse sizing in cases of high inrush currents is to select a fuse that has a continuous current rating higher than the expected inrush current, but not so high that it would fail to protect the circuit from short circuits or overloads. Several factors should be considered, including the continuous current rating of the servo motors, the expected inrush current of the servo motors, and any recommended fuse sizes. Consider a scenario involving a 10 kV amps transformer powering two CNC machines with servo motors. The inrush current is a key consideration when selecting the appropriate fuse size. The purpose of a fuse is to protect the circuit from overcurrent conditions, including both short circuits and overloads. A fuse that is too small will blow prematurely due to the high inrush current, leading to unnecessary downtime. A fuse that is too large will not provide adequate protection against smaller overloads, potentially damaging the equipment. The selection of the appropriate fuse size requires careful consideration of the continuous current rating of the servo motors and the magnitude and duration of the inrush current. Servo motors typically draw significantly higher current during startup than during normal operation. This inrush current can be several times the continuous current rating of the motor. The fuse must be able to withstand this inrush current without blowing, while still providing protection against sustained overloads. Firstly, determine the continuous current rating of the servo motors. This information is typically found on the motor's nameplate or in the manufacturer's specifications. Secondly, determine the expected inrush current of the servo motors. This information may also be found in the manufacturer's specifications or can be estimated based on the motor's design. Thirdly, select a fuse that has a continuous current rating higher than the continuous current rating of the servo motors. The fuse should also be able to withstand the expected inrush current without blowing. Fuse manufacturers typically provide time current curves that show the amount of time it takes for a fuse to blow at different current levels. These curves can be used to select a fuse that will withstand the inrush current for the required duration. Consider the transformer's capacity and its ability to handle inrush currents. A 10 kV amps transformer has a limited capacity, and excessive inrush currents can overload the transformer and cause it to overheat or fail. The transformer's impedance also plays a role in limiting the inrush current. A higher impedance transformer will limit the inrush current more effectively, but it may also result in a lower voltage during startup. The National Electrical Code, or NEC, provides guidelines for overcurrent protection of electrical equipment, including transformers and motors. NEC Section 430.52 provides specific requirements for motor circuit protection, including fuse sizing. The NEC allows for the use of time delay fuses, which are designed to withstand temporary overloads such as inrush currents, without blowing. Time delay fuses are often recommended for motor circuits because they can provide both overload and short circuit protection. The NEC also allows for the use of inverse time circuit breakers, which are similar to time delay fuses in that they are designed to withstand temporary overloads. Inverse time circuit breakers trip faster as the current increases, providing better protection against short circuits. In selecting the appropriate fuse or circuit breaker, it is important to consider the specific requirements of the application and the recommendations of the equipment manufacturers. Using the correct fuse size is crucial for protecting equipment and ensuring safe operation. Undersized fuses will cause nuisance tripping, while oversized fuses may not provide adequate protection against overloads and short circuits. The information provided here is for general guidance only, and it is always recommended to consult with a qualified electrical engineer to determine the appropriate fuse size for a specific application. Fuses protect electrical circuits from overcurrent conditions. They contain a metal wire or strip that melts and breaks the circuit when the current exceeds a certain level. Fuses are rated in amps, which indicates the amount of current they can carry before blowing. Selecting the right fuse size is crucial for electrical safety and equipment protection. An undersized fuse will blow prematurely, causing unnecessary downtime. An oversized fuse may not protect the circuit from overloads, potentially leading to equipment damage or even fire. To determine the correct fuse size, consider the following factors. Firstly, calculate the load current. This is the amount of current that the circuit is expected to carry under normal operating conditions. You can calculate the load current by dividing the power in watts by the voltage. Secondly, determine the inrush current. This is the surge of current that occurs when an electrical device is first turned on. Inrush current can be significantly higher than the load current, especially for motors and transformers. Thirdly, apply a safety factor. It is generally recommended to use a fuse that is rated at least 125% of the load current. This provides a margin of safety to prevent nuisance tripping. Fourthly, consider the fuse type. There are different types of fuses available, each with its own characteristics. Time delay fuses are designed to withstand temporary overloads, such as inrush currents, without blowing. They are often used for motor circuits and other applications where inrush current is a concern. Fast-acting fuses are designed to blow quickly in response to an overcurrent. They are typically used for sensitive electronic circuits where rapid protection is required. After calculating the load current, determining the inrush current, applying a safety factor, and considering the fuse type, select a fuse that meets all of the requirements. It is always better to err on the side of caution and choose a fuse that is slightly larger than necessary. However, do not use a fuse that is so large that it will not protect the circuit from overloads. If you are unsure about the correct fuse size, consult with a qualified electrician. Replacing a fuse with the wrong size can be dangerous and could damage your equipment or cause a fire. The selection of fuses for servo motor circuits involves several key considerations to ensure both reliable operation and adequate protection. Firstly, understanding the motor's characteristics is crucial. Servo motors, especially those used in CNC machines, often exhibit high inrush currents during startup or rapid acceleration. This inrush current can be significantly higher than the motor's continuous current rating. Therefore, the fuse must be able to withstand this temporary surge without blowing, while still providing protection against sustained overloads or short circuits. Secondly, consider the different types of fuses available. Time delay fuses, also known as slow blow fuses, are specifically designed for applications with high inrush currents. These fuses have a built-in delay that allows them to tolerate short duration overloads without interrupting the circuit. This makes them suitable for servo motor circuits where the inrush current is a common occurrence. Fast-acting fuses, on the other hand, are designed to blow quickly in response to an overcurrent. While they offer excellent protection against short circuits, they may be prone to nuisance tripping in servo motor circuits due to the inrush current. Thirdly, consult the motor manufacturer's specifications. The motor manufacturer typically provides recommendations for the appropriate fuse size and type for their motors. These recommendations are based on the motor's electrical characteristics and operating conditions. Following the manufacturer's recommendations is essential for ensuring both motor protection and reliable operation. Fourthly, refer to relevant electrical codes and standards. Electrical codes, such as the NEC, provide guidelines for overcurrent protection of electrical equipment, including motors. These codes specify the maximum allowable fuse size based on the motor's full load current rating. Complying with these codes is mandatory for ensuring electrical safety. Fifthly, calculate the motor's full load current. The motor's full load current, also known as the rated current, is the amount of current the motor draws when operating at its rated horsepower and voltage. This information is typically found on the motor's nameplate. Calculating the full load current is necessary for determining the appropriate fuse size. Sixthly, apply a safety factor. It is common practice to apply a safety factor to the calculated full load current to account for variations in operating conditions and to prevent nuisance tripping. A safety factor of 125% is often used, meaning the fuse size should be at least 1.25 times the motor's full load current. Seventhly, consider the transformer's capacity. If the servo motors are powered by a transformer, the transformer's capacity must be sufficient to handle the inrush current of the motors. The transformer's impedance also plays a role in limiting the inrush current. Eighthly, coordinate the fuse with other protective devices. In some cases, multiple protective devices such as fuses and circuit breakers may be used in a circuit. It is important to coordinate these devices so that they work together to provide adequate protection. This involves selecting devices with appropriate time current characteristics so that the upstream device does not trip before the downstream device. Ninthly, test the installation. After the fuses have been installed, it is important to test the installation to ensure that the fuses are functioning properly. This can be done by simulating an overcurrent condition and verifying that the fuses trip as expected. Tenthly, document the fuse selection. It is important to document the fuse selection process, including the motor's characteristics, the calculations performed, and the rationale for choosing the specific fuse size and type. This documentation can be helpful for future maintenance and troubleshooting. In summary, selecting fuses for servo motor circuits requires a thorough understanding of the motor's characteristics, the available fuse types, relevant electrical codes and standards, and proper calculation methods. By following these guidelines, you can ensure both reliable operation and adequate protection for your servo motor circuits. For the 10 kV amps transformer, consider the primary and secondary voltages. For example, if the primary voltage is 480 volts and the secondary voltage is 208 volts, you would need to calculate the primary and secondary currents. The transformer's impedance also affects the fault current and thus the fuse selection. Remember to account for the transformer's inrush current as well, which is typically much higher than the full load current. When calculating the fuse size for the primary side of the transformer, consider the transformer's full load amps, or FLA, and the allowable overcurrent protection according to the NEC, specifically Table 450.3. The primary fuse protects the transformer itself, while the secondary fuse protects the load connected to the transformer, in this case the servo motors. You must also consider the interrupting rating of the fuse. The interrupting rating is the maximum fault current that the fuse can safely interrupt. The interrupting rating of the fuse must be greater than the available fault current at the fuse location. The available fault current can be calculated using a fault current calculator or by performing a fault current study. In addition to fuses, circuit breakers can also be used for overcurrent protection. Circuit breakers have several advantages over fuses, including the ability to be reset after a trip and the availability of adjustable trip settings. However, circuit breakers can also be more expensive than fuses. When selecting a circuit breaker, it is important to consider the same factors as when selecting a fuse, including the load current, the inrush current, the interrupting rating, and the coordination with other protective devices. Furthermore, the type of load being served should be considered. Motors, for instance, often require time delay fuses or inverse time circuit breakers to accommodate their starting currents. Resistive loads, on the other hand, can typically be protected with standard fuses or circuit breakers. Also, consider the ambient temperature in which the fuse or circuit breaker will be installed. High ambient temperatures can affect the performance of these devices, and it may be necessary to derate them accordingly. Ensure that all electrical work is performed by qualified personnel in accordance with all applicable codes and standards. Incorrectly sized or installed overcurrent protection devices can create a significant safety hazard. Remember that proper fuse selection is not just about protecting the equipment. It is also about protecting people from electrical hazards. So take the time to do it right. Using larger fuses can be acceptable, but it's important to understand the implications and ensure that it doesn't compromise the overall safety and protection of the circuit.